at some other school where they want him.
Alright, so today, talking about energy and work and the relationship between energy and work and power. How are all those related? Well, at the end of last semester, we finished up talking about forces. And that is going to be our springboard when talking about work done. And we can't talk about work until we talk about energy. Okay? In order to do work, what do you need?
Energy.
Energy. Right? Which will produce some type of force. Okay? So, energy. Just the ability to do work. Right? Now, there's a whole list of our types of energies. What would be a type of energy? On.
Potential energy.
Potential energy, that's right. What is another type, Alana?
Kinetic energy.
Kinetic energy. Now, a lot of these energy types are subtypes of energy, okay? So, kinetic energy, which is just our energy of motion. So anything that's moving is going to have kinetic energy. Okay, so it is a very broad type of energy, and there are energy types that are subcategories of that we'll talk about. One of the subcategories, a car moves with what type of energy? A bicycle, same thing. Okay, well, it's kinetic, but with what type of kinetic energy?
Potential.
Work.
It uses potential energy to transform to... No, it starts with an M. What's a bike, a wheel, a lever, a pulley? What are all of those? Screw, wedge.
They're machines.
Simple machine. So what type of energy?
Mechanic energy.
Mechanical. Close enough. Mechanical energy. Now, mechanical energy is a subgroup of kinetic, right? Because mechanical energy is energy of motion. It just happens to be done by a machine.
So mechanical energy is also kinetic energy?
It is a type of kinetic energy, yes. You guys see the paper clip grasshoppers?
No,
When you drop these on the table? That was dead. What type of energy was that?
That was
Before I dropped it.
potential.
Potential! Potential energy. Stored energy, right? So when its little legs are crossed, that's stored energy. And then when I drop it, it releases that stored energy. Now there's two types, and we'll talk about both of these. Hold on a second. There's gravitational, and then there's elastic. Okay? Gravitational is real simple. If you push something off your table, what happens? It falls. That's all gravitational potential is. It means it's off the floor. So if it goes off the edge of an object and falls to the ground, that's gravitational. It just means that it's lifted off the ground. Elastic is just like the paperclip. Okay? It has stored energy, or a spring, right? If I have this makeshift spring and I squeeze it, it's going to want to return back to its former state. Yes.
I have two questions.
Number one.
Are there more types of kinetic energy?
Yes.
And the second one for potential, what kind of potential energy would a roller coaster at the top of the drop in the gas station?
Yes.
Gravitation.
Gravitation.
That can cause a really interesting
Nigel?
If you did one of those rollback cars, whenever you were rolling it back, would it have potential energy?
Yes.
Or kind of like a roller coaster, where you could potentially go down its kinetic.
That's exactly right. And we'll have some diagrams over that in a second. What type of energy is food? Nigel?
Chemical energy.
Chemical energy. Exactly right. So, you guys have to eat food, and that food gets broken down in your cells and mitochondria, and it converts it to energy. Very, very simple, but in that process it releases an electron. Okay? Well, that electron is what allows your muscles to work, right? Your muscles work on electricity. That is your brain. That's why if you get tased, what happens to your muscles? Yeah, they get short-circuited, right? If all your muscles work on electrons, electricity, if I put a taser on you, all of your muscles are going to get short-circuited, so they'll tense up. That's why if you ever see someone get tased, they go, ah! And just kind of like fall over, right? What's another example of chemical energy? Food was one. What's another one? Chemical energy. Okay, that could be a food, a drink. You're mixing chemicals. Everyday life. How did you get to school today? Okay, a car. What does a car use? Gas. Gas is has chemical potential energy, right? So this is a chemical potential.
And it's
It's
not
a
because
potential energy.
it doesn't work until the like engine's on.
That's right. It's stored energy, right? So it doesn't use that energy until it is reacted in some way. Nigel?
Can I use that one food energy example for my little brother because it's sometimes?
Yes. Thermal. Heat. Now, if you guys want to get rich, I have everyone's attention immediately. Come up with a machine that has that produces zero thermal energy. Okay? That will produce zero heat, yes. A machine that produces zero heat. That's right. The reason is because all machines have moving parts, and anytime you have a moving part, you have friction. Anytime you have friction, you have heat, and that heat's wasted. Okay? Even without moving parts. Say, take an incandescent light bulb. Right? The old school round light bulbs. If that's on for, say, 5 minutes and you touch it, what happens? It's hot, right? So where does that heat come from?
Energy that's moving through the wire to the light bulb.
Okay? Is that heat necessary? No, it's wasted. Okay, so all of this electricity is going through that little filament, right, that pops and breaks and goes off. So all that electricity, a whole bunch of electricity, gets shoved in a really thin wire. So think of it like this. Think of rush hour traffic on the interstate. All those cars. 4 lanes of traffic. All of a sudden, construction goes down to 1 lane. Okay, that's what happens to these electrons. So you have all this big pack, 4 lanes. All of a sudden, you have 1 lane of traffic. What happens to the drivers?
They get stopped.
They get stopped, and what else?
Angry.
They get mad. Well, the same kind of thing what happens in a light bulb. Not really. They don't really get mad, but as a byproduct, all of this heat gets released. All of this waste. Okay? all this because of the thinness of the wire, and we'll talk about this resistance wires whenever we get into our electricity unit. But all of this electricity, because the wire is so thin, gets turned into heat and light. Okay, that's why it produces light, which is great. But also one of the byproducts is all this heat it's wasted. So all that heat is just wasting your electricity. With like any machine, if you have heat coming off of something, that is wasted transformation of energy. Okay, so like in a car, you have gasoline. Gasoline goes from that chemical to kinetic energy, right? For the car moving. Well, there's also all kinds of heat being put off. All that is inefficient, wasted heat. Sound is our next type. Now, when you think of sound, you're just thinking of the music, talking. However, if you harness the power of sound, you can have a powerful weapon. Over the last 10 years or so, off the east coast of Africa, Somalia, there are a lot of Somalis pirates running around. Now, these aren't eye patch, parrot, and Armady. They, not quite.
They don't have a plane.
Yeah, they have automatic weapons and run up to like a cargo boat and hijack it and then hold them for ransom. Well, these are business cargo boats, right, Taylor?
Yes.
So they can't have military weapons like guns and.
Well, they could, but it'd be illegal.
Why they can't.
So one of the options that they've come up with is, and I think this came out of DARPA, our military think tank, is a sound weapon, which produces a super intense, high frequency noise that is funneled in one direction. So it's kind of like a spotlight, but instead of high intensity light, it's high intensity sound.
Is the frequency low enough to where humans can hear it?
No, it's super high, so it hears it and it hurts. It's so loud and intense that it hurts. So what they have these on the bow of the boat. So when the pirates come, they point this weapon at them, and it is you can hear it. It's super high frequency. It's like
Your head is also big.
So it's high enough.
Humans can hear it.
well, no, not that. I mean, high enough to where we can hear it, but debilitating, like a real high pitched squeak. Who can do a high pitched squeak?
Alexis.
No, I don't want to hear it. Never mind. No. Yeah, that's true. Yeah. Think of Schwadre, but amplified times 1,000,000. And that's what this is. Pointed at you. It's horrible, horrible. So this prevents the pirates boarding and they live another day. Moving on. Light energy. Now, whenever you guys think of light, you think about visible light. Well, light in the electromagnetic spectrum encompasses everything from X-rays to gamma rays to TV and radio waves, everything. That's the whole spectrum, with a whole bunch of stuff in between. So light energy is not just visible light, although that's one very small segment, what we can see, but infrared is another one. Each of these will be their own unit later on in the semester. And of course, you can separate our visible light using a prism.
Is that the new pizza? What? Prism does.
We'll be doing lab with prism as well. Of course, one of our favorites, electrical energy. Think how your daily life would be different without electricity. Catastrophic.
I would die. Me?
Actually, I play Minecraft.
I just need a channel.
And finally, what's the last one?
How is low energy?
Ended World War II.
Nuclear.
That's right. The assassination of the Bishop of Poland or whatever.
World War II is like energies, right?
Yes.
Okay.
Something to do with Poland. Jeremy, do you remember what started World War II?
Invaded Poland.
No, there was.
Because they didn't pull a big from the sausage.
That could be it. All right, moving on.
Yes, I did.
So is that where like atom smashing and splitting the atoms and all that kinds of thing? Why did they think splitting the atom would end the universe?
Because I didn't know.
Why is there a boom?
Can you see it, Adam?
Because this is not
Do we have the technology? Yeah.
To an electron microscope, yeah.
We did it in Cody class. You know what I did?
A cell, maybe.
I was on the
All right, work. Focusing. Now, in order to do work, what do we need?
The pencil, John.
Energy.
Energy. That's right. And more importantly,
During a distance.
when you calculate work, you have to figure out how much force is used and over what distance. So what's your equation? W equals FD. W equals force times distance.
Is force capital F?
Yes, force is capital F. Work is capital W. D is lowercase or distance. Yes.
Should work ever do like ever be done and stop? It doesn't move.
Has to be there has to be motion.
What?
That's the definition.
I took a picture of someone. I was playing so much.
In our unit for work is joules, capital J.
For work?
Yes, for work. And actually, as you'll figure out, that's the same unit for energy as well. Is the man who studied work and energy was named Jules. Last name?
They should name the unit Taylor.
Alright, so let's do an example. What is that?
A pea.
A cucumber.
Corn.
A pickle.
What?
Is it a overgrown?
It's an acorn, of course.
Working out.
So, how much work will an acorn do when it lifts 230 Newton barbell? So, write down your question, your equation, calculate. Mark has already drawn his equation triangle for work. Fantastic, Mark. What's our equation?
W equals FP.
Okay, W equals FT. You know your force, you know your distance, right?
So this is 2.
So what do we get as an answer? 460 joules. 460 joules.
Is it capital J?
It is a capital J, yes. It is a capital J.
What's capital G?
Any questions on that? All right, what happens if we were to lift it 3 meters?
You have to go.
And as you're doing that, think about the relationship between force and work. Think back what our two types of relationships are to begin with. So what do we get?
690 joules.
690 joules?
Yes.
Okay? Questions on that? Real simple, right? Okay, good. If we were to double the weight of the barbell, 460 newtons, what happens to the amount of work? It doesn't matter. Double the weight, what happens to the work? It doubles?
Are we using 3 meters or 2 meters?
It doesn't matter.
It doubles.
It doubles? Okay, obviously it's higher. Why does it double?
Because force and work are directly proportional.
Fantastic. Because force and work are directly proportional. Remember, they're on opposite sides of the equation, so when one goes up, the other one has to go up. Directly proportional. Yes?
Is it any force of weight or all forces are?
In this equation, all forces are. Okay? Good about that? Moving on. All right, so let's talk about work and the direction that the force is applied. So, what is a vector? Nigel?
It's a point with direction and magnitude.
That's right. It's a line. It's an arrow, basically. That's all a vector is. It's an arrow. The direction and magnitude. So, when we're talking about this, we have to make sure that the distance traveled and the force applied are in the same direction. Because if they're not, then there's no work done. Okay, so the distance traveled and the force applied have to be in the same direction.
So they have to be the same direction.
Yes.
Same thing.
Same direction, the same way.
So they have to be in the same direction. And the same direction? Or that's the same?
That's the same. Yeah, their arrows have to be going the same way. So if your force arrow goes one way and the direction of motion goes the other, then there's no work. Okay? For example, there's this guy holding this boulder. Okay? Which direction is the force going? Applied to the boulder. Up. Okay, so the force is going up. If he were to slide to the right like that, the distance vector is going to go to the right. Correct?
Yes.
Is there work done?
Yes.
No. There's no work done because our vectors are going in different directions. Now, if he were to climb a flight of stairs, okay, then that would be up. And there would be work done. Or if we were to say how much work was done when he picked it off the ground, then there would be work done. But him just holding it and moving to the right, there's zero work. Yeah.
So technically, like moving furniture around in the house, you're technically not doing anything.
That's right.
So
But if you're loading in the back of a truck, then you are.
there's still force applied onto the boulder.
Yes. Alright. Power. Anyone know what power is?
I used to.
What do you think, Mike?
How much force?
Okay. Close. It has to do with force applied. What did we just talk about? Work, right? We just talked about work? Okay, so all power is how much work is done in the amount of time it takes. So it's basically work per second. How much work can you do in a second? So if you're already done writing, you are more powerful than the person who's still writing, as far as writing notes goes.
Yeah. You're right.
Our equation. What do you think our equation is going to be? Nigel?
Work times time. Work over time.
Y over.
I don't think you're right how much it is.
What's our operative word in this sentence?
Per.
Per. That's right. Per. So, work over time.
Can I clear something?
Sure.
Power is just P.
It can just be capital P, yes. Anyone know what our unit is for power?
Joules over second.
Anyone know what joules per second transforms to?
Energy.
Anyone know what's the unit for power?
We don't know.
You guys just don't know what's the unit for power?
Watts.
Watts! Yay! What's the unit for power?
I get it. I've never seen Watt. That was there.
What's the problem?
Watts. He said it to me. Alright.
A watt is a capital W.
What's your capital?
Yep. Yes.
Did you say that the same unit of water is
Joules is the same unit for work and for energy, not power. Yes, good catch. Yes.
And how does Watts work for light?
Oh, we're going to talk about that.
Of course.
Right now?
We're going to end here.
No! It's time to go?
Fun.
Almost. I was hoping